Okay, let's get started. So did you start lab 1 already? So who started lab 1? Oh, great. So how do you feel it? Okay?
Yeah, using the software is not too bad. I'm still kind of stuck on the pre-lab.
Okay.
Pre-lab questions, so I might try to swing by your office or something.
Yeah, no problem. How about you? So do you think it's okay?
Yeah, the pre-lab was kind of confusing.
Yeah, and just follow the steps. I think it should be fine. So it's not real programming yet. You just need to put blocks together. So I think it should be pretty much okay. Yeah, let me know if you have any questions. I just uploaded homework 1, and it will be due on February the 10th. I think it's next Monday. Okay, just a bunch of questions, and there are some problems from the textbook. So I also uploaded those questions. So if you don't have the textbook, I think still be okay, right? But it's better to have the textbook. So by the way, so do you have the textbook, the 5th edition of? Yeah, I think so. The problems number are from the 5th edition. I think in the 4th edition you can get the same thing, but it's better to have the 5th edition. Okay, great. Yeah, let me know if you have any questions about the homework and the labs. Okay. Yeah, and the videos are still under process, so I think I'm going to upload everything by the weekend. So if you missed lectures, you can watch the video during the weekend. All right. Okay. So yeah, let's briefly overview what we covered in the last lecture. So we're still in the procedure of reviewing the concept in the signals and system, right? And gradually, we're going to relate those concepts to wireless communication, and you'll see how, so basically, wireless communication is exact an application of signal system, okay? All right, so yeah, we introduced the Fourier series for periodic signal, okay? And the first, the starting point is that we assume our signal x of t or s of t is real and periodic, right? And because the real signal is easier to analyze, and by this assumption, and we can write down the Fourier series for the real version, right? And we have the synthesis equation, and we have the analysis equation, right? So basically, so this is a form, right? So yeah, those are just like for the historic point of view, so everything starts from here, right? But in reality, we don't really use it, right? But in your lab, it's kind of using that because in the lab, we have the real signal and we have a symmetric signal, okay? And then basically only have the real part, you don't have the imaginary part, yeah. Okay, so as we said in the class, so we don't really like this form because this form, so for each k, we have 2 terms, right? So it's not exactly what we want, right? So because of this, so we introduced the concept of the complex exponential Fourier series, right? So one of the reasons we introduced Fourier series is to answer those questions, right? So what are the frequency components of a signal? Okay, and how can we determine the range of the signal in terms of the frequency domain, right? So that's the reason we introduced the concept of the Fourier domain analysis. Okay, and in order to do this, we have 2 cases. So one case is for the periodic signal. The other case is for aperiodic signal, right? So it turns out that so the analysis is much easier for the periodic signal. So everything starts from the analysis of the periodic signal, okay? And for periodic signal, so we can define this kind of basis, right? So basically, so I have this f1 here. So we're going to use f0, for simplicity because we use t0 here. The reason we use f1 here is that it basically means it's 1 times the fundamental frequency of the periodic signal x of t or s of t, right? And so those define the basis. So here, so we have 1 times the fundamental frequency, and we can have other bases in this form. So such that we have different frequency components like this, right? I have Gn here. So it's basically the signal only, the basis only defines as a multiple n times the fundamental frequency, which is 1 over T naught, right? Okay, great. And in this case, and by doing this, so we can write the Fourier series, right, like as the original signal, equals to a summation of one Fourier coefficient multiplied all the bases here. Okay, so this is a complex exponential Fourier series, and we call that the inverse transform because if we know S of n, right, all the Fourier coefficients, and we know the fundamental frequency, which is 1 over T naught or F naught, we can write the original signal. Okay, it's kind of the inverse transform, right? The Fourier transform is from the time domain to the frequency domain, but here is the vice versa, from the frequency domain to the time domain. Okay, and here is how we can compute the Fourier coefficients, right? We just use some inner product between this original signal and each basis, right? And compute this inner product, and here is a normalization, right? And then doing this, so we could get the formula for the Fourier coefficients, okay? And after some manipulation, so this is what we got, right? So basically what we do is that we do an integral over one period. Here, for simplicity, we just do the integral over one fundamental period, right? And then we use the original signal multiply the exponential of this guy, okay? And by doing this, we get the Fourier coefficient. And remember, as we said, the Fourier coefficient is a signal, represent a signal in the frequency domain, okay? And in particular, for the periodic signal, we only have the component at multiples of the fundamental frequency, okay? N times F naught, basically, right, for all integer n. All right, so it is possible that for some of the components we have 0, right, as we've seen maybe in your lab 1, okay? And we call that forward transform because, so here we can compute the signal from the time domain to the frequency domain, right? That's why we call that forward transform. If you know Fourier transform, you can see that's exactly, analogy to the Fourier transform, okay? That we're going to talk about later. And here we can see that. So basically for the Fourier series, we need all the components here, right? But if we don't have all the components, right, we just have the first few components. So we can still more or less recover the original signal, right? Here's an example for a square wave form. If I have two terms, and the green curve is what we can get, right? And that is kind of similar to the blue signal, right? But with some difference because we don't have all the frequency component, right? And from here, you can also see that, right? So this transition here is not as sharp as this, right? Because we're lacking of the higher frequency component, right? Higher frequency meaning sudden change, right? So we don't have this sudden change, so we have this more smooth transition. Similar here, right? So we have this more smoother transition, and we cannot have this sudden change. In order to describe this, this like really fast change, we need all the frequency components, okay? And yeah, and here is an example, and in your lab, you're gonna have something very similar to this, right, but different, okay? And so we can, using the formula, we could compute the Fourier series coefficients like this, okay? And we can plot that. So we need to be a little bit careful here. So in this case, it's very lucky that all the coefficients here are real. So there's no complex number here, right? So the reason of that is, so you can analyze that offline, right? But the reason of that is the original signal is real first, and then it is even, okay? For real and even, and we can show that its Fourier coefficients are also real and even, okay? And then, so this is, we can plot its Fourier coefficients like this, right? And for this guy, we can understand this as the signal in the frequency domain, okay? And for each component, so this describes how much of the signal in this particular frequency, okay? And we can see for some of the frequency, it is 0. It means that signal does not have this frequency component, right? And for some of them, they are not 0, okay? And one very interesting behavior is that for a signal that is periodic and a continuous time in the time domain, and then in the frequency domain, so that's discrete and aperiodic. Okay, it's the exact opposite, so which is kind of interesting. Yes?
What's the x-axis on the bottom graph?
This guy
Yeah.
is frequency.
Okay.
So yeah, we can, you can think that just like f, the frequency. And for each point here, so that represents the multiples of the fundamental frequency. Yeah, good question. Is that clear? Okay, great. Yeah, and here's a summary, right? So we have the analysis equation for the complex Fourier series, and we have the synthesis equation for the complex exponential Fourier series. Okay, and here's the sufficient condition for the existence of the Fourier series, right? And so just we covered that before. I will not repeat it. So the only thing we need to remember here is that they are sufficient, but not necessary. There are millions of counterexamples, right? So I can tell you why we still need that, but that is for later, right? When we determine a property of a system, so those properties are very important. But for now, it's not that important. Yes?
Can you go back to the previous slide?
Of course. Yeah.
This is true for periodic and even, or just periodic?
Just periodic. Yeah, not for even. The S of t can be anything. Can be complex for sure. Yeah, good question. Yeah, it's just like if x of t is real and even, so we can have more property about Sn, right? But there's no constraint for S of t. Besides, it should satisfy those conditions, or not. So, good. Okay, other questions? Yeah, I'm kind of going very fast, right? Just stop me if you have any questions. So those basic concepts are pretty important. And then we come to talk about the system, right? So what we study for the system is the linear time invariant system, okay? And we assume, and so the goal is to study what is the relationship between the output signal and input signal when the system is linear time invariant. And h of t denotes the impulse response of the system. It basically means that when the input is delta t, direct delta t, and then the output is h of t, right? So that's the meaning of h, okay? And then we went through the derivation of the convolution, right? So this is the definition of the linearity, and this is the definition of the time invariant, right? And we talk details about what exact meaning of linearity and time invariant is. And here is an example about system, right? So a system like if y equals to a times x plus b, right? We need to be careful of this. So in general, that is not linear system, right? It's a fine system. When b is 0, that's linear, okay? And then we went to the derivation of the convolution, right? So basically, one thing I want to emphasize here is that the convolution is not a definition, right? It's not like, okay, so we have a LTI system, so we define convolution like that, right? It's not a definition, it's a result, right? It's a result of an LTI system, okay? And here's the derivation. So basically, we use the sampling property of delta function. We use this formula to represent x itself, okay? And then here we use the linearity. We move h from outside to inside, and then we use the time invariant property, right, to change this guy to h of t, right? And you can see, so this is the definition of convolution, okay? So for any LTI system, convolution is what is really happening there, okay? And then we plug our periodic signal S of t in this convolution, right? And this is what we get, okay? So if we take a deeper look at this, and this is what we have, okay? So let's denote h of f like this. So this is actually a Fourier transform that we're going to talk about later, right? So we don't need to worry too much about it. Just consider that as a definition. So basically, what we have for the output is that R of t output equals to this guy, right? If we compare this and that, compare the output and input, right? S is the input, RT is the output, right? They're almost identical, except this guy, right? Therefore, you can see that the only thing happening for a periodic signal passing through an LTI system is that we multiply a coefficients determined by the system, right? And that's it, right? So here I have S of n, here I have Sn times this, right? That's the only thing happening for an LTI system, so which is very nice. Okay, and here, yeah, basically I want to emphasize the same thing here, right? So one nice thing here, so why is it so nice? So consider a signal that, right? So let's say we only have one component of Sn. Yeah, question?
Can you explain again the previous slide?
Of course. Yeah, so basically, what I want you to see is that compare this guy and that guy, right? If you compare this and that, the only difference you can see that is for the output, we have an additional term here, right? And that's it. There's no other difference. Okay, so basically, it means that when a periodic signal passing through an LTI system, so we multiply each frequency component by this guy. Okay, so this is extremely important. It's very simple, right? Think about this. If we only have one term here, let's say we only have n equals to whatever, and every other term is 0. For example, n equals to 1, right? So when as n equals to 1, it basically means that our input is just one complex exponential, right? The output will be just this complex exponential multiply this guy. That's it. Okay, so it's just a multiplication, relationship. It's very nice, right? So one application of that is think about if this is our input signal, and then if we can observe the output, we just need to use the output divide the input to get the channel coefficients, or the system is basically the channel in wireless communication. Okay, then we can estimate the channel. It's an extremely easy way to do that, and this is what we use in practice in 4G, 5G, Wi-Fi, everywhere. It's that simple. Okay, yes.
So like in a case like that, are you saying that like the channel is the LTI system?
Channel of what system? OTI, LTI.
Yeah, so the channel would be the LTI system.
Yes.
that you're putting input.
Exactly. Yeah, normally, if you want to estimate the channel, you need to do a deconvolution. That's hard, right? But here, just multiplication, right? So it sounds very, very simple, right? So why it is so advanced? Because 4G, 5G, Wi-Fi 6, Wi-Fi 7, they're all using this concept, right? So it's not that easy to use in practice. Why is that? The reason is that look at this signal, the complex exponential. It's a periodic signal. The periodic signal does not exist in reality. So it has to go from minus infinity to infinity, to plus infinity. It has to last forever. But in practice, we don't have this kind of signal. Therefore, we need to play some trick. So that's why this kind of wireless communication is so advanced. We have some trick there to make this happen in practice. Okay? And that will be the last topic of this class, right? So if you really want to learn that, you have to stay until the last. Okay, but it's a very cool concept. Okay, great. And okay, so this is what I talk about basically. So what I talk about is that the complex exponential is so-called eigenfunction, meaning that if that is the input, so the output of a system would be the original signal multiplied a constant c. So this constant c is determined by the system. Okay, it's called eigenfunction. So that it's like, I think you all learned eigenfunction, eigenvalue from your linear algebra class, right? This is the same thing, right? In your linear algebra, what is eigenfunction or eigenvalue, right? When the input is a vector, and then you multiply that by a matrix, and then the output is like this vector multiplied a constant. Right, the same thing here. The only difference here is that the operation is not like a vector multiply a matrix. It's a convolution. It's still a linear operator, by the way. Right? Actually, conceptually, there's no difference compared to the eigenfunction and the eigenvector and the eigenvalue learned in linear algebra. Okay, great. Yeah, and here, so let's go back to one interesting concept. So as we said, we use this formula to compute h of f. It turns out that so this is Fourier transform, okay? So it's very similar to a Fourier series computation. The only difference here is that, so now the f is continuous. It's not multiples of your fundamental frequency anymore. It's continuous, okay? So now let me ask you one question. So we have seen Fourier series, right? So why we need the concept of Fourier transform? Because this is not signal system class, right? I definitely skip all the relationship and the derivation, but do you still remember? So why we need Fourier transform? So we have the Fourier series, right? Great. But why we need another transform? Yeah, right? Why we define Fourier transform? Yeah, let me give you a hint, right? So we emphasized multiple times that the Fourier series is defined for periodic signal, right? When you want to compute the Fourier series, remember you need to you need to know the fundamental frequency or fundamental period of a signal. That's omega naught, f naught, or t naught, right? And so that's very important, right? So Fourier series is only defined for periodic signal. Okay, and that's why the periodic signal is easy to analyze, right? So we didn't cover too much here, but there are many, many nice properties of the Fourier transform. Fourier series. Okay, so what if we want to apply the same or similar property of the Fourier series to aperiodic signal? What should we do? Okay, so can we define something similar, like the Fourier series, for aperiodic signal? Right? Obviously, the answer is yes. Right? So we can derive Fourier transform. So actually, so this guy is from the Fourier. The derivation of this guy is from the Fourier series. How can we do that? So how can we make a periodic signal aperiodic?
I know like the periodic extension is that the
It's the other way, right? But that's correct, right? So periodic extension basically means that, okay, so if we have a periodic, if I have an aperiodic signal, let's say we have a square waveform, okay, then we can just repeat it, right? So that's the definition of the periodic signal. We just repeat it, and so on, to make it periodic, right? Then, so for this guy, we can do the Fourier series, right? But now we want to do a Fourier series for this guy. What should we do? How can we, transfer this guy to this?
Band limit it, like band limit it using like a filter.
Yeah, let's say this is a time domain. Yeah.
You just take one period.
Yeah, but mathematically, what should I do? Right, let's say here's 0, here's t naught. T naught is the period of the signal. So mathematically, we just let t naught goes to infinity. Right, meaning the distance between these two guys becomes larger and larger. This doesn't change, right? We just make the distance become this larger and larger. When t naught goes to infinity, then we have an aperiodic signal. Do you agree? All of you? Right, because what's the definition of periodic signal, right? So meaning that it repeats itself, for a finite amount, right? So if it repeats itself at the infinite point, it means that it doesn't repeat, right? Does that make sense? Yeah, basically, we just write down the Fourier series definition, and then let t naught go to infinity, and then we can get this formula. Okay, that's how we derive it. That's simple. Okay. So that's why we start everything from the periodic signal, right? Because that is easy to analyze, and then we can, get the similar stuff from periodic to aperiodic. Does that make sense? Okay. So now let's take a formal look at the Fourier transform. Okay. Non-periodic signal. So basically, for the aperiodic signal, so we still need to define the base function, right? So unlike before, so now, so this is our base function. So before it's 2 pi times, it's n, 2 pi times n times f naught, right? So the base function is only defined for discrete frequency point, n times f naught. But for aperiodic signal, so we need to use that. So f is the real domain, right? So the reason is nothing but this t naught goes to the infinity, right? Think about this, right? So before, our frequency component for the Fourier series is n over t naught or n times f naught, right? So now when t naught goes to infinity, so 1 over f naught becomes extremely small. Therefore, n times something extremely small becomes a real number. That makes sense? Right? N is integer. When n times something extremely, extremely small, then it can cover all the real numbers, right? That makes sense? Yeah, hopefully it did, right? So n multiplies something really small. It can be whatever, right? Then it can cover all the real numbers. That's how we get this, right? So now f is nothing but in the real domain. It's a real number now, okay? And by using that, we can write down the definition of the Fourier transform, okay? So the Fourier transform is nothing but, again, so we have our signal multiply, not multiply, compute the signal, the inner product between the signal and the base, and then we get our definition for the Fourier transform, okay? And you can see, so this is almost identical as the computation of the Fourier series coefficients, right? The only difference is that now f is real, and f is real before f is n times f naught. Okay, that's the only difference, right? Okay, and we can have our inverse transform, right? Meaning that we can reconstruct our original signal from its Fourier transform. Okay, and this is the formula for the inverse transform. And for the inverse transform, we have two versions. So one version is use f. So the unit of f is hertz. The other version is using omega. So the unit of omega is rad, right? The relationship between f and omega, again, is that omega equals to 2 pi times f, right? If you replace 2 pi f here, then the 2 pi here and here can be canceled, right? So we have this, okay? So they are the same. Okay, in practice, I think we use that because we don't have the coefficient in front, right, which is more convenient. Okay, so that's the inverse Fourier transform. Okay, yeah, that's explain what I just explained, right? So normally in practice, we don't want this 1 over 2 pi in front, and for the Fourier transform, normally we're using this double arrow to represent its Fourier transform pair, right? This is the time domain signal, and this is the frequency domain signal. Okay. All right. And the last bullet is that, so we can see that the formula of the forward and inverse transform is almost identical, right? If we see this again, so this is the inverse transform, right? So it's h of f multiply exponential of j 2 pi ft, right? So the forward transform is almost identical, but the only difference here is that we have this minus sign here, right? That's the only difference, right? Therefore, you can see the forward and inverse transform are almost identical, okay, in terms of computation. Okay, and here's one important property of the Fourier transform. So we can think the Fourier transform as a system, right? What the system does is just some manipulation on the signal, right? If we consider the Fourier transform as a system, so we can show that, so this system is linear, right? And here is the definition, right? If I have a linear combination of the input signal, and then we do the Fourier transform of this guy, we can show that it equals to, the signal, do the Fourier transform first, and then do the multiplication, and then do the sum, okay? The Fourier transform is, this operator is linear, right? That makes sense? Okay, great. And this is to finish talking about the concept of the last lecture. So we have some leftovers. So now let's see what we can do for today, right? So we're going to continue on this. So basically, we're going to talk about these topics. The first is the energy. So what happened if an energy signal passing through an LTI system, right? So before, what we talk about is it's a periodic signal, right, which is a power signal, right? But now, what if an energy signal passing through a system, right? Let's see what happened. And the other thing is that, so we have seen negative frequency a few times, right? But what's the meaning of the negative frequency, right? Frequencies should be positive, right? It should be hertz, right? So what does -1 hertz mean? Okay, so we're going to give some explanation on that. And then we're going to see some common Fourier transform, so focus on delta signals. So and then we're going to see a frequency shifting property. So among all other properties, so this property is the most important property that we're going to use all the time in wireless communication, right? So basically, we're just shift the signal in the frequency domain quite a bit, right? We only need to determine where to shift the signal. Okay, so we're going to see that in the next lecture for some examples. Okay, and so now let's talk about energy signal in LTI system. So we let S to be an energy signal, and we denote S of F to be its Fourier transform. Okay, so remember now we're talking about energy signal. Okay, and when we talk about energy signal, meaning that the energy is bigger than 0 and less than infinity, and we let S of t to input into an LTI system, and we denote H as before. We denote HT as the impulse response of a system, and its Fourier transform is determined by H of F. Okay, again, H of t is the output of an LTI system when the input is a delta signal. Okay, that's the definition of H of t. All right, and now let's do some derivation here. So yeah, we can write the output of signal, which is RT, as the convolution between the input and the impulse response of a system, H of t. Okay, and from here we can just do some manipulation. So basically, what we do here in the first step, we write the inverse Fourier transform of this guy, right? Represent that using the Fourier transform. Okay, this is the definition of the inverse transform, right? Remember, for the inverse transform, this sign is plus. Okay, for the Fourier transform, this sign will be minus. So now we have a plus sign, and this is what we have. So now the trick that we do is that we exchange the order of the integral. Okay, so we exchange f and u. So f is the frequency domain, and u is in the time domain. Okay, we exchange the order. So we do the integral over u first, right? Then we can take everything related to f out of the first integral, right? So we can see h of f is not a function of u, and this guy is not a function of u. We take these two out, and here is the inside. Okay, and from this, what is that? So what is this integral? The time domain signal multiply the complex exponential, and we have a minus sign here. So what is that? Fourier transform, right? So we can write comfortably S of f here, and we have h as h of f times S of f, right? Together, multiply this guy, right? This guy is complex exponential with a positive sign here, right? This guy is basically the inverse Fourier transform of this multiplication, okay? And this is what we get, right? From here, we can see that the output, the time domain signal of the output equals to the inverse Fourier transform of h of f times S of f. So basically, it means that in the frequency domain, RF, so RF is the frequency domain signal of RT, that equals to h of f times S of f, right? So that's a very important property of the Fourier transform. So in the time domain, we do a convolution, right, which is hard to do, right? But in the frequency domain, what is really happening is a multiplication. We just need to use the Fourier transform of the input, multiply the Fourier transform of the channel of the system, and then we can get the Fourier transform of the output signal, right? So does that make sense? Yeah. So basically, in practice, so this is what we normally do, right? Because the time domain convolution is always harder to do compared to this modification in the frequency domain, right? Normally, there's one special case that convolution can be easier. Can you imagine what case we want to do a convolution? We don't want to do a modification. Yeah, we're gonna, yes.
If the signals are really short.
Very good. Almost, right? If a signal is delta signal, and then do a convolution is very easy, right? So yeah, very good. We're gonna do that in the next lecture. So you're gonna see. Okay, great. And now let's talk about the negative frequency, right? So yeah, before that, maybe I want to emphasize one more thing here. So yeah, let's recall that the idea to introduce the Fourier transform is that we want to have the similar property of the Fourier series as for the periodic signal, right? But later on, so we're going to see that. So we don't want so many transforms, right? Fourier series is one transform, and the Fourier transform is another transform. So we don't want two transforms. We just want one transform. How about that, right? So it basically means that can we do Fourier transform for periodic signal? Right, that valid question. So it turns out that sometimes we can. Okay, so therefore in practice, so if you work in the wireless industry, normally we don't talk about Fourier series at all. So everything people talk about is Fourier transform. Because in practice, for the signal that we care about, we can do Fourier transform for periodic signal, right? But this Fourier transform has to be weird, right? Because Fourier transform is introduced for aperiodic signal. How come we can do that for periodic signal, right? By the way, for the Fourier transform, we also have a list of the sufficient convergence conditions. I didn't list there. We have a Dirichlet condition for Fourier transform as well. So one condition is that the signal has to be absolutely integrable. Obviously, for a periodic signal, it doesn't happen, right? But sometimes we can still do that. How can we do that? So it's under the help of delta signal. Okay, so we're gonna see that in the next lecture. Yeah, but just want to say a word on that. Okay, great. So now let's see the negative frequency. So what's the meaning of the negative frequency? Okay, so in the book there's some explanation, right? So basically, I didn't list it here. So in the book you can read section 2.9.2. So basically in the book, what it explained is that so the frequency component only means the variations, how fast the signal will vary in the time domain. That makes sense, right? And if we think about sine and cosine, right? If we put a negative sign in front of it, for example, if we put a negative sign in front of cosine, it doesn't matter, right? In the sine, it matters a little bit. But if we think that in the complex exponential, let's say e j 2 pi ft, think in this way, right? So yeah, let me remove it. Right, for this guy, so basically this guy is defined on a unit circle, right? Because the norm of it, or the magnitude of it is 1. It's a cosine and sine, right? And so if we change t, so we can think, so it will rotate in this way. Okay, if we put a negative sign here, it will rotate in this way. Okay, so rotation is kind of opposite, right? So that's kind of the mathematical meaning of it. Right? Basically, the conclusion is that the frequency minus frequency component does not have a real physical meaning there. Okay, so frequency is a positive thing, and only the absolute value of the frequency have some meaning, meaning how fast the signal will change. That makes sense, somehow, right? But I think for us, it really doesn't matter. So how here is another way to understand this problem, right? Let's see what I wrote down here. So basically, if we consider a signal in the time domain, g of t, so that's real, right? So later on, we will consider a complex signal, but yeah, but let's say so our signal, our transmit signal, or the input signal, g of t is a real signal. Okay, so now let's compute what exactly happened when we consider negative frequency, right? So we put a negative sign here. So GF is nothing but the Fourier transform of GT, okay? And we put a negative sign in front of it. So let's see what's the meaning of it, okay? And here we just put the negative sign in front of the frequency, right? We have negative sign here, and we have negative sign here. So this is the definition of the Fourier transform, and we have a plus sign here, okay? And now. So yeah, let's write the signal in this way, okay? We take a conjugate out, right? If we take conjugate out here, then the plus sign has to be negative, and then we write a conjugate sign on the g. Okay, we do a conjugation, right? Because the g is real, then g conjugate and g has to be the same. Okay, and then we'll arrive here, And this guy is nothing but the Fourier transform of g of t. And then if we write this guy in this way, so we can have, so if we put the negative sign here, and what happens is that, so this guy will equals to gf naught conjugate. And here f is positive. Right? What does that mean? Right? So if g is real, g negative f naught equals to g conjugate f naught. So what's the meaning of it? It's kind of symmetric in some way, right? But what else we can observe from it? Right? Meaning that if we know gf naught without any computation, we know g minus f naught, right? So gf minus naught, g minus f naught can be completely determined by gf, right? So meaning the negative component does not carry additional information, right? If we throw the negative part away, we're fine, right? Because we can recover it exactly by using the positive frequency component, right? Meaning the negative frequency really doesn't matter for the real GT, right? Therefore, we don't need to worry too much about the negative frequency because it doesn't carry any additional information. Does that make sense? Yeah, here's another view of this. Okay, and another view of this is that, okay, so now how about we make GT as a periodic signal, okay, and then compute the synthesis formula of it, right? Because now it basically means that let's assume this guy is the coefficient of the Fourier series, okay? Make it periodic, right? We're going to show that we can really do that, okay? And then for this part we have to multiply this, and for this part we have to multiply this, right? Consider f naught is the fundamental frequency, and then after some manipulation using the top relationship, what we can get is that, yeah, maybe let's go over it. So basically from here to here, we just write the conjugate version of it, okay? And then we take the conjugate out, and we can get, so why it always happen? We take the conjugate out, and this is what we get. And if we have a complex number plus its conjugate, and then only the real part left, okay? And then we can write it down using the Euler's formula, okay? So basically, it means that so if it's kind of obvious, right? So the meaning of it is we just derive, if we write the synthesis equation to get GT, the periodic version of GT should be real, right? That's our assumption. Right? Do you see where I'm getting, right? So basically, if we write the positive frequency component add the negative frequency component and also multiply its corresponding the complex exponential, then we're going to get a real signal. Okay, that explains why the signal is real. Does that make sense? Okay, here just a different understanding, different view of the negative frequency. Right, the conclusion is that, okay, still the positive frequency makes a lot of sense, so just worry about that for now. Right, does that make sense? Any questions? Yes?
So are you kind of saying, like, if G of t is real, then you have the quality is true there, and then also the other way? So, like, if the Fourier transform coefficient of the negative frequency is the conjugate of the positive frequency, then the signal must be real?
Yes, you just verify that. Yeah. Right, it's like, okay, if GT is real, then we'll have the top relationship, and if we have the top relationship, GT is real. Yeah, something like that. Okay, just some manipulation of the Fourier transform and so on. Okay. Yeah, so here is just repeating what I just said, right? So we only care about the real. When we measure the bandwidth of signal, we only care about the real part, and so we don't worry about the negative part. Okay, great. Okay, now let's see some important Fourier transform. So one important Fourier transform is delta signal. If we do a Fourier transform of a delta signal, and then, so And then we get this definition. How can we get from here to here? Right? Why we get this guy from this guy? So that's the multiplication property of a delta signal, right? Imagine, so this is a signal multiply a function, right? This integral just equals to this function evaluated at t equals to 0, right? It's a multiplication property of a delta signal, right? If we plug 0 in here, we'll just get 1, right? So this basically means that, for delta signal, we have an extremely fast change in the time domain, right? And then in the frequency domain, so it has to cover all the frequency component and at equal amount, right? So this match frequency component is to use to describe this behavior, this saddle up and saddle down. Okay, because it's changing so fast, and then the change from 0 to infinity, right? It changes so fast, and then we need from minus infinity to plus infinity frequency components to describe this behavior. Okay, kind of makes sense. All right, and here, so basically we say if a system response is a delta signal, and then in the frequency domain it's just 1, right? So basically it means that the system does nothing. Right? So if I have a signal passing through a system, and the system is a delta signal, it's a delta function. Right? Delta is a convolution identity. Right? If x of t convolutes delta t equals to xt itself. Right? And in the frequency domain, so h of f is 1. Right? So basically means that in the frequency domain, we have x of f or s of f multiply 1, nothing happened. Right? It kind of makes sense to consider that is a system. Okay. Okay, great. Next one is that if we have a shift on delta signal, right? If delta signal shift by f naught, and then what happened in the frequency domain? So again, so how can we get this? Is that we use the multiplication property of a delta signal, right? We just plug f naught into this equation to get this. Okay, and this is our Fourier transform. The delta of f plus f naught will just equals to a complex exponential. Yes?
The delta function having a magnitude of 1 in the frequency domain, is that just like a property of the delta function?
Yeah, because we just compute it, right? So we compute the Fourier transform of delta signal, and then this is what we get. Yeah, it's a property of the delta. You can think that as a property of the delta signal. Okay, good. Any other questions? Okay, great. And now let's recall some, we have seen that before, right? Euler's formula, right? So complex exponential just equals to cosine plus j times sine, right? And if we put a minus sign here, and we have cosine minus j times sine, right? So now, what if, so we do a Fourier transform of this guy and see what we get, right? We just learned that the shifted delta signal, the Fourier transform of that, is nothing but the complex exponential, right? And by doing this inverse Fourier transform, so we get cosine. In other words, the Fourier transform of the cosine equals to this guy. Is that weird? So remember, as we said before, so this is a Fourier transform. It's designed for aperiodic signal. But cosine signal is periodic, and we can still do Fourier transform. The reason we can still do that is by the introduction of the direct delta signal. Right? That's kind of weird, right? It seems natural, but it's very weird. Okay, we're going to have a much deeper look about this in the next lecture, right? So we're out of time. So we're going to continue in the next lecture. Okay? Thank you. See you on Friday.